Hey, folks. Today's topic, we're talking about some expression stuff, some algebra stuff that we haven't seen in a while, or maybe you haven't seen in a while. So I just want to kind of talk about what Corpy's point of this lesson is. So calculus is really about two things: how fast something is changing in a moment, called an instantaneous rate of change, which is division, and then the area of weird shapes, which is multiplication. So basically, and I'll talk more about that, trust me, calculus is about, at the end of the day, calculus itself is just basically about multiplying and dividing. The calculus is not usually the tough part, and I think if you have Roop, he says something similar to this. The thing that makes calculus such a challenging course is not the calculus, but the tedious algebra. Okay, so the algebra is what the important skill that you're going to see. You're going to have to be able to manage. He calls this algebraic gymnastics. I think kind of a nice idea. The sort of ability to look at something and kind of follow I call it your math voice. Kind of follow what your math voice says. So you can read some more here if you want to. Basically, the idea is we do a lot of simplifying to make something more condensed and easier to work with. So here are some of his tricks, some of the things he wants to highlight. I think these are all good things. Look for a common factor. If you had Mr. Wojo back in the day, or even I use it most of the time, is we talk about GCF, or factor out is probably what I say the most. Wojo says is GCF. Probably his is better because you're doing the greatest common factor. So always when you look at something, is there something that I can take out? Then you've got your things. These are memorized. These are things that you should know by heart, especially this one. I would say dopes would be, I call that dopes, difference of perfect squares. These are different color. This one, I don't see this one as much because we could just use regular factoring and then we would get this. This is a shortcut. It's maybe worth memorizing. Sum and difference of cubes, I don't know if I would say that's worth memorizing. I have it on my board. If I think back to my notes and homework, I don't think it shows up really all that often. And when it does, we can just kind of look it up. Some synthetic division, that's a big one. I don't know if you remember synthetic, or I'm going to put or long division. We're going to cover that again in this set of notes. So that's the topic. That's the idea. What we're trying to do is we're trying to make stuff look nicer algebraically. So let's take a look at a couple examples. So this is what I mean. Like, you look at this, it just says simplify. Like, what does that mean? That's where your math voice comes in, and what he calls algebraic gymnastics. You got to look at this and recognize that there's stuff you can do. I don't know how else to say it. It's just your math voice. My math voice looks at this and I think factoring. Anytime I see an x with a power and a regular x, or x's that are unlike terms, I think of factoring. And so as I look at this, I notice that I could do some factoring out of the numerator. So if I take this, I can take out an x. That leaves behind an x squared minus 9. Over this, then, is what I would call x factoring. If you remember how to x factor, there's a couple different ways to do it. I would do the first thing times the last thing, which is 12, positive 12, with a negative 7 underneath. Then I would find two factors that multiply to make positive 12 and add to make negative 7. That's negative 3 and negative 4. Then from here, there's two ways to factor this. There's the figure it out method. And this one's so easy. I'm not going to go into much more detail here. So this turns out to be x minus 3 and x minus 4. If you don't know how to factor, you and I should talk. Now, if you notice, you might say, okay, well, there's still nothing to clean up here. And you're right. If you don't clean it up more, there isn't anything to clean up. But you have to recognize, and you always have to ask yourself, can I do more? And in this case, we can do more. X squared minus 9 can factor again into x plus 3 and x minus 3. Now, what do you notice cancels? Boom and boom. And we're left with x times the quantity x plus 3 over x minus 4. And then from here we could apply some stuff. I mean, we could start to do, if you remember back what we talked about in P2, we could start to talk about some HAs and VAs or zeros, and we could analyze it if we had to, but we're going to stop there. Simplify. Okay, so this one, again, I'm thinking factor. When I look at this, I think factor because I've got different kinds of x's on like terms. This to me is a factor by parts, and I know that because it has 4 terms. Now, it doesn't mean that that's going to work, but that's what I'm thinking is going to happen. So when you factor by parts, you might remember we want to group these into 2 separate parts. We want to think of this as a part, and we want to think of this as a part. Notice what I did there? I left the minus open. That's because whatever this is always factors out. So as I look at these first 2 terms, what do these 2 things have in common? Well, they have a 4 and an x. That leaves behind an x. Let me try again. It has a 4 and an x squared. Excuse me. That leaves behind an x and a minus 2. No matter what, that minus sign must come out. It doesn't matter if the second term has it or not. That's the term, that's the sign that has to come out. 20 and 40 have a 20 in common. And then that leaves behind an x. And now remember, you took out a negative 20. That leaves behind a positive x. You took out a negative 20. That leaves behind a negative 2. And if you remember, I know I probably did this right because those 2 chunks are the same. So I now have 4x squared minus 20 as one of my pieces, and then the other piece is x minus 2 over 2x minus 4. And here we are again. It doesn't feel like anything cancels. That's because we're not remembering that we should factor out if possible. So as I look at this, I notice this term has a 4 in common. So I can factor out 4 times x squared minus 5 times the quantity x minus 2. That's what we call a prime binomial. 2x minus 4, I can factor something out here. I don't know how to get you to recognize that. That's one of the skills that you have to catch on your own. So then from here, I would clean this up. Now I notice that my x minus 2's cancel. I also notice that my 4 over 2 cancels, and I'm left with 2 times the quantity x squared minus 5. And we actually could break this down even further if we wanted to. You can factor this. This isn't dopes, but this is still, you can break it down like we did dopes. I mean, how did you come up with from 9? How did you turn it into a 3 and a 3? Well, you square rooted 9 and got 3. So this can actually factor again into 2 times the quantity x plus root 5 and x minus root 5. Now, how do you know which one do you want as your answer? Well, it depends on the situation. Depends on what you're trying to do with it. Let's say you're trying to figure out the zeros. So then maybe it would be nicer to factor this to find the zeros, and then you could just ZPP each piece of this. But if you ZPP'd this and solved it, you would still get plus or minus root 5 once you try to solve that. So it doesn't really matter. I want to go back up here, and I want to talk about how to reduce just as a reminder. So let's say that I didn't cancel the 4 and the 2, but I did cancel the x minus 2 and the x minus 4. So that would leave me with 4 times the quantity x squared minus 5 over 2. Now I'm going to distribute, which would be 4x squared minus 20 over 2. Let me just remind you that this is reducible. And it's reducible because this and this have the same common factor as this and this. It has to be something that goes into all of those pieces. 4 and 20 and 2 are all divisible by 2, so I can clean this up and have 2x squared minus 10. And then I could factor out, or I could leave it, like I said, depending on the situation. But this does not work. Let's say this was 4x squared minus, let's do 4x squared minus 21 over 3. This does not reduce. These 2 do not have anything in common. Even though these do, it's not good enough overall to be able to reduce that. because it has to be something that goes into all of them. I mean, here's another one that I was just thinking of. Let's say that you had, what could I do? Let's do 6. No. Let's do 18x squared minus, dang it. Hold on, I'm going to think of a better one. Maybe pause for a second. All right, I got a good one. So let's say we had 8x plus 15 over 6. So 8 and 6 have something in common. They're both divisible by 2. 15 and 6 have something in common. They're both divisible by 3, but there's not something in common with all of them. So we can't actually clean that up at all. So these two are both sad faces. We wouldn't be able to simplify these two anymore. We are able to simplify this one again because it all the terms have something in common. All right, so next up we have these things that are called complex fractions. That's when you have a fraction within another fraction. And the way I get rid of them, there's lots of different ways to do it where you try to find a common denominator and combine like terms. All I do is I try to find the least common multiple that I could do to kill all the fractions off. Whenever I see a fraction, I try to eliminate the fraction. So what could I times by that would kill off an x? Well, I could times by x. I have to times by a 5. I have to times by x squared. And I have to times by 25. So if I wanted to, I could times by all of this. That would work. But what's nicer is to look at this and take the least amount of stuff that you could multiply by that would kill off all these denominators at once. So the least thing, well, 25 would make 5 and 25 happy, and x squared would make x and x squared happy. So I'm going to multiply the top by 25x squared. Now, whatever you do to the top, of course, you have to do to the bottom. So I'm going to multiply the bottom by 25x squared. So really, what am I multiplying by? I'm multiplying by 1, which means I'm not changing the value of anything. I'm just changing the way it looks. Now I'm going to distribute. Now when I distribute, I'm going to distribute this to each one of these. So that means I'm going to do 25x squared times 1 over x. So that's going to end up in the numerator. So this is going to end up being 25x squared on the top. Now what I do, though, is before I do that, I just think about what's going to cancel out. So if I have 25x squared over x, one of those x's is going to cancel out. So I'll get 25x. Minus, now I'm going to do 25x squared to the top, then divide by 5. Well, when I divide 25 by 5, I'll get a 5, and I still have the x squared. Over, same thing on the bottom, 25x squared times 1. The x squared part is going to cancel out this time. 25x squared over 25, the 25 is going to cancel out, leaves us with the x squared. Okay, here's our next trick. And you might remember this from pre-calc. When something, to me, this is backwards. I want it to be, to me, this is dopes, but it's dopes that's backwards. I want the x squared to be in front. It doesn't have to be, but I want the x squared to be in front. Now, I can't just magically switch it around, because if I did, I mean, think about it. Is 6 minus 7 the same as 7 minus 6? No, that's called the commutative property. 6 plus 7 equals 7 plus 6. That does work. So if this was an add, I could just switch them around and still would have the same value. But because it's a subtract, it's not going to have the same value. But what are these off by? 6 take away 7, negative 1. 7 take away 6, positive. They're off just by a negative. So whenever something is backwards, factor out a negative 1. So on the top and on the bottom here, I'm going to factor out a negative 1. So I now have negative 1 times the quantity. Well, if I take out a negative, that means that this part now is the positive part. Oh, I should have taken out a negative. I'm going to take out a negative 5, sorry, because I noticed these also have a 5 in common. So when I take out a negative 5, that's going to make this thing become a positive x squared. When I take out a negative 5, oh, I could take out even more than that. God darn it, I'm way off here. Let's try again. Let's do the bottom first. I think that's what I should focus on. So I'm going to take out a negative 1. So now the negative x squared is going to become the positive x squared. The positive 25 is going to become the negative 25. Now the numerator, let's do a little bit more legwork so I don't have to do all this scribbling out again. I'm going to take out a negative because it's backwards. 25 and 5 share a 5. X and x squared share an x. So that's what I'm going to factor out. So that's going to now make this part become the positive part. I took out a negative, a 5, and an x. So that's just going to leave behind an x. I took out a negative, so that's going to make this negative. I took out a 5, that's going to make that a 5. I took out an x. That means it's not going to have an x. All right, so now we look at this and say, can we do more? The answer is yes. The numerator, though, I can't. But the denominator, this is dopes. Negative 1 times x plus 5 and x minus 5. All right, so now let's try to clean this thing up. A couple things I notice. I've got a negative and a negative. I've got a minus x minus 5 and an x minus 5. So that leaves us with 5x over x plus 5. Now, suddenly I can tell you a lot of things about my function. I can tell you that it has an HA of y equals 5. I can tell you that it has a vertical asymptote of x equals negative 5. I can tell you that it has a 0 at 0. I can tell you that it has a y-intercept of 0. I mean, all this stuff now I could figure out that I couldn't tell you anything about my function in this spot. Okay, a couple of things to remember. These are fractional exponents. So fractional exponents can turn into roots. And it doesn't matter which way you write it. You can do the root first or you can do the power first. So if I were to kind of organize this the way that I like to show it, I would say something like this. A to the m over n. This becomes the exponent. This becomes the root. So this would turn into the nth root of a to the m. I also want to remind you that a negative exponent means flip. I don't like to say negative exponent means put it on the bottom because it depends. If the negative exponent is already on the bottom, it's going to flip to the top. And so I think this is a nice little example that he shows here of all the kind of trickiness that can be shown, the way that we can condense things mathematically and what they really mean if you were trying to calculate something. So first of all, this is the number 1/2. And then we had a root of 3. So that went on the bottom of my exponent. And we had an exponent of 2. That went on the top of my exponent. So if you don't already know this, this is very much worth memorizing. This is a big deal. It's one of those things that'll pop up over and over and over again. So if we get something like this, we try to simplify it, try to make it look nicer. It looks pretty nasty to begin with, but just take care of a little bit at a time. So the biggest thing that's jumping out to me is that I've got these negative exponents. So that means it's going to flip to the bottom, but you have to be careful. This is going to flip to the bottom, but it's going to flip to the bottom of this term. Because 3 is connected to this by subtract. I can't jump this all the way to the bottom of the whole thing because the whole top is separated. So this 3 plays a role which kind of blocks this from being able to flip to the bottom. So how does it clean up then? Let's take a look. So I'm going to do what's called a rewrite, and we do this a lot in this class. I'm going to rewrite it so it looks like a little bit nicer form. So I have 3 subtract. Now I'm going to put this thing in the denominator. Of the 6. This is still over 6 minus. Why don't you try to rewrite the second part? Hit pause real quick. Okay, let's see how you did. So that's going to be the 12x will be on the top, and we get x squared minus 4 on the bottom. Okay, from here, what do you do? How do you clean this thing up? Well, you got to do a little bit more legwork. Right away, I noticed that the 3 and the 6 feel like they should cancel, but they don't, because I don't have something, well, kind of do, but it's harder to see right now. But right now, though, you can't just cancel these two without taking into account these. Now, if you wanted to, you could divide this by 3, that 6 by 3, and that 12 by 3. That would actually be legal, but you still would have a 1 there. So I'm not going to sweat that right now. What I am going to sweat is the fraction within a fraction. So I want to figure out what could I times by that would make these two things happy. Well, let's take a look. The top is, I can't make that look any better. X minus 2 is x minus 2. But x squared minus 4, that's dopes. So this factors into x plus 2 and x minus 2. So now what's the least amount of stuff to multiply by that would make both of these denominators happy? Well, luckily they already share the x minus 2, but this guy needs an x plus 2. Now I can't pick and choose. If I'm going to times this by x plus 2 and x minus 2, I have to times the top by x plus 2 and x minus 2. Let's say for a minute that this was x minus 7. Well, I would still have to do x plus 2 and x minus 2, but then I would also have to do an x plus 7 to clean it up. All right, so now what does this thing look like when we clean it up? I'm actually going to jump down here, I think. So this thing is going to get distributed to the 3, and then it's going to get distributed to the fraction. So I'm going to have 3 times x plus 2, x minus 2, minus 6. Now, one of these is going to cancel, though, when I distribute it in. When I distribute, the x minus 2's are going to undo each other, and I'm just going to have an x plus 2. Over, this thing needs to get distributed to the 6. And then when I do this to distribute, this is really nice. Both of them are going to cancel out, so I'm just going to have a minus 12x. Now we're going to start to clean up. And this is where using previous information will really help you out. X squared plus, or x plus 2, x minus 2 is the same as x squared minus 4. So here, I already know what this is going to expand to be. This is x squared minus 4. This is x squared minus 4. So when I distribute, I can save myself a little bit of work. So 3 times x squared is 3x squared. 3 times minus 4 is minus 12. And then I'm going to take the negative 6 and distribute it. Minus 6 minus 12. Over, I'm going to take this 6, I'm going to distribute it. That's 6x squared minus 24 minus 12x. I can see that something goes into all these, but I'm not going to worry about that right now. I just want to organize my like terms. So 3x squared minus 6x minus 12 is minus 24 over 6x squared minus 12x minus 24. Okay, now let's see if there's something that we can factor out. So I ran out of room again, so I'm going to jump down here. Everything is divisible by 3 on the top, so I'm going to divide the top by 3. 3 times x squared minus 2x minus 8 over everything in the denominator is divisible by 6. It's going to leave behind x squared minus 2x minus 4. I know those are going to cancel, but I'm going to worry about that at the end. Let's see, can we factor this? My math voice says to factor this. So 3, okay, minus 4, that makes 2. That'd be x minus 4, x plus 2. This would be 6. This would be x minus 4, x plus 2 again. No. Yeah. What did I do before that? Is this right? 3x plus 2 minus 4. Yeah, that looks good. No. This has to be a... Wait, x squared minus 2 minus 4? That's not factorable, is it? Because think about it, they have to have different signs to make the 4, so that's 2 and 2. But then when they add them up, oh, this is not factorable. So we would go back and say, all right, what we had before is the best we can do. So I'm going to divide out that. Now I'm going to cancel out that 3 over 6, make that a 2. So our best cleaned up answer would be x squared minus 2x minus 8 over 2x squared minus 4x minus 8. That's as cleaned up as you could get. So this would be one of those, if you asked me to sketch this, I would have some issues. I mean, I could figure out the HA, it's a tie, so the HA is y equals 1/2. My y-intercept is positive 1. But other than that, I don't know where my VAs are or I don't know where my VAs or my zeros are. Okay, let's do one more, and then we'll pause. Maybe we'll do 2 more and try to get through example 6, because they're both kind of go together. So this is what we're talking about. This is called rationalizing. I don't know if you remember that from our where is it? Does it say? There we go. This is called rationalization. It's basically the idea of trying to get the root off the bottom. We did this a lot in trig. So if I want to kill off these roots, so if I want to be able to get rid of the roots here, this is not exactly a great trick, but it's not a great problem to ask you just to rationalize this. So what we would do is we'd multiply by what's called the conjugate. And the conjugate occurs anytime you want to square something, and you can't just do squares. I can't just square this and have it. It's not the same thing. I mean, put some numbers in there and see. You'll find out that this does not work. If you just magically square it, it's not going to give you the same answer. So what I'm going to do is I'm going to times by the conjugate. The conjugate is the exact same thing, except we change the sign in the middle. So it's still root x plus 3. It's still root 3, but there's a sign in the middle. Over square root x plus 3 plus square root x plus 3. Now, you don't have a choice there. Whatever you do to the top, you got to do to the bottom. Now, here's where the real power in the conjugate comes from. Watch what happens to my numerator. I'm going to take this and I'm going to start to distribute. Root x plus 3 times root x plus 3. The roots cancel out, and I get x plus 3. Now, I'm going to distribute this one to this one. It's going to be something crappy. I don't know what it is. I don't even care what it is, but I know it's going to be a mess. But it's going to be a positive mess. And then I'm going to distribute this one to this one. It's going to be the same mess, but it's going to be a negative mess. So these two undo each other. They cancel each other out. They add up to 0, so I don't even worry about them. Now then I'm going to take this one. I'm going to distribute it to that one. So what's a negative root 3 times a positive root 3? That's a negative 3. Look at what happened. All of a sudden, our roots are gone in the numerator. Now you might say, well, wait, now we made the denominator a mess. But I'll show you why that's okay. And you might remember it from the spring last year when we did the the intro to calculus lesson in pre-calc. So I got plus 3 and minus 3 cancel each other out. Now that leaves me with an x on the top times the quantity x, or over the x times the quantity x plus 3 plus root 3. Then what happens to our x's? Those cancel out, and we're left with 1 over x plus 3 under a root. Now you might say, wait a minute, I've got roots on the bottom. This is bad news. Yeah, that's true. But the reason you would ever do this is because you would do the limit. We would actually evaluate the limit of this. So I would take the limit as x approaches 0 of square root x plus 3 minus over x. Why can't we just figure that out? Well, if I put a 0 in the bottom, what happens? It blows up. But after we do all this algebra, I would have that the limit as x approaches 0 of 1 over x plus 3 plus root 3. Now, look what happens. Now, when I take the 0 and I plug it in for x, I get 1 over root 3 plus root 3, which is equal to 1 over 2 roots of 3, which is something that we can now kind of quantify in our head what that number is. So I don't have a great answer for you here. Sometimes we leave roots on the bottom and sometimes we don't. Like, for instance, in this next example, we're not going to leave the root on the bottom. So here we go. I need to get this root off the bottom. So what I'm going to do is I'm going to multiply by the conjugate. What's the conjugate? Let's have you try this one. So you've got 4 over 1 minus root 5. And you're going to try to get the root off the bottom. Okay, so hopefully you started off by multiplying by the conjugate. So the conjugate of 1 minus root 5 is 1 plus root 5. So the numerator is now a mess. But I can at least clean it up a little bit. So 4 times 1 is 4. 4 times root 5 is 4 root 5. Over, and then I'm going to distribute this, and that mathemagic is going to happen again. 1 times 1, okay, well that's 1. 1 times root 5 is root 5. Negative root 5 times 1 is negative root 5. Those two things are going to cancel each other out. They're going to add up to 0. And then I'm going to do negative root 5 times positive root 5, which would be negative 5. This is something that we can now clean up even further. 4 plus 4 over root 5. My bad. 4 plus 4 root 5 over 1 minus 5 is negative 4. Notice everything is divisible by 4, and I've got a negative on the bottom. Negative on the bottom is super easy to fix. All I'm going to do is bump it to the top, and then I'm going to divide everything by 4. So that'd be negative 1 minus root 5. Notice I had to put the negative with both of them to get to my final spot. Okay, so I'll stop here for this part, and then you can watch the next video for the rest of the notes.